Okay. So, now here you have to understand actually like very I mean computation easy, but very high, but I will show you one or two things. For example, let a cost function, this is capital F suffix capital N x, right, to be defined as follows, right. So, F capital F, we are using capital F as small f, that is why I am telling that capital F suffix N x is the minimum cost in rupees per hour, say, or maybe dollar per hour also, no problem, or any other currency unit, does not matter, right. The minimum cost in rupees per hour of generating x megawatt by n units, right. So, this is the minimum cost, right. So, that is we are making at capital F n x is equal to minimum cost in rupees per hour of generating x megawatt by n units, right. This is one, and small f capital N suffix y is equal to cost of generating y megawatt by the nth unit, right. Right, this is the meaning, it is megawatt by n units and this is actually nth unit, right. So, therefore, equation is very simple, you just will look, then therefore, capital F n minus 1 x minus y, that is your the minimum cost of generating x minus y megawatt, right. Here we are where we are taking that nomenclature is like this, that capital F suffix n x, the minimum cost in rupees per hour of generating x megawatt by n units, right. And here small f capital N y is equal to cost of generating y megawatt by the nth unit. If it is your y megawatt generated by this your what you call by the nth unit, then remaining n minus 1 unit, that is capital F n minus 1, it and remaining megawatt will be x minus y, that is the minimum cost of generating x minus y megawatt. This is the meaning by the remaining n minus 1 units, right. So, now the application of dynamic programming result in the following recursive relation, that is capital F n x, right, is equal to minimize y, right, f n y is small f capital N suffix y plus n is the unit number, right, capital F n minus 1 x minus y. This equation is very simple, no. When you look it is nothing actually, no mathematics like these two equations, but very complicated actually, right. I mean very or what you call very computationally we have to spend lot of time. For example, use just I will show you how things are. Using the above recursive relation, we can easily determine the combination of units yielding minimum operating cost for loads ranging in convenience step from the minimum permissible load to the smallest unit to the sum of the capacities of all the available units, right. So, using this equation only we will make it that what will be the your what you call that optimum combination of the unit and minimum cost. In this process, the total minimum operating cost and the load shared by each unit of the optimal combination are automatically determined for each load level. Question is that here you have to go for a discrete step, right. Had it been soft computing technique, things are very easier actually, right. Only thing is several constants are there, it may be time consuming, but coding point of view that soft computing technique is very easier, right. But in any way those are beyond the scope. But suppose this is a table number is not given, these generating parameters are given. Though this parameter there are 4 units, right, 1, 2, 3, 4, there are 4 units, and capacity is every generator is minimum capacity generating capacity is 1 megawatt and maximum is 12 megawatt. So, for all these things minimum is 1, maximum is 12, right. And cost curve parameters A is given rupees per megawatt megawatt square and B is rupees per megawatt, C term is not here, right. So, that means the cost curve is actually A Pg square plus B Pg, this is the form because it is rupees per megawatt square. So, it will be A because you have to your objective function should be in terms of rupees. So, it will be A into Pg square plus B, that we have seen for optimal operation in power system, of course, there C was there, right. But question is that here C is neglected, right, only A and B we have taken, and these are the A values for unit 1, unit 2, unit 3, unit 4, and this is B value for unit 1, unit 2, unit 3 and unit 4, right. So, now you have to consider a sample system, that is a sample system, that is a 4 unit system, right. All 4 are thermal generating units, that parameters also given, I have told you, right. Now, it is required to determine the most economical units to be committed for a load of 9. Suppose your total load demand is 9 megawatt, then you have to find out of these 4 units which are most economical, right. So, and but their minimum generation is, listen, idea is something like this, right. So, here there are 4 units, So, if all the units are operating, say, then total minimum generation will be 4 megawatt if you add all, and maximum generation, if you all are operating, that the total maximum will be 48 megawatt, because 12 into 4, 48 megawatt, right. But anyway, it is supplying just 9 megawatt, right. So, we have to see, sometimes 1 unit is possible, because maximum is 12, 1 unit can, whether it is economical or not, or 2 units also possible, 3 units also possible, 4 unit also possible, right. But we have to see the which combination, right. So, in this case, first one is that your F1x, suppose let the load changes be steps in 1 megawatt, we are changing the load step change is 1 megawatt only, right. That means, if 1 unit generating 9 megawatt, another unit generate 0 megawatt, if 0 9, then 1 8, then 2 7, then 3 6, like this way combination you have to take. If you take less than that, your accuracy will increase, but computational effort will be much more, right. So, now capital F1x, that is the first unit, right. That means, suppose this numbering is arbitrary, you can take any number, it does not matter, right. So, first unit, this first unit, say, when n is equal to 1, capital F1x, right, is equal to small f1x, right, is equal to A1 Pg1 square plus B1 Pg1. Now, Pg1 actually is a 9 megawatt. Suppose when unit 1 is generating, say, all the 9 megawatt, right. So, in that case, your F19, capital F19 is equal to small f19 is equal to your A1 is 0.3855 from this table, 0.385, and B1 is 23.5, because it is A1, B1, A2, B2, A3, B3, A4, B4. In general, we have given A and B's, right. So, in that case, it is 0.385 into 9 square plus 23.5 into 9, and that is coming actually rupees 242.685 per hour. It is coming. Although I can take this paise thing, we can eliminate. No need actually, you can make it approximately 243, but for the sake of mathematics I have written this, right. From the recursive relation, that is equation 1, right, from the recursive relation, this is your equation 1, right. I mean this equation, from this equation, this recursive relation, this equation, right. From this equation you can make it like this, you can make it like this, that computation is made for F20, capital F20, capital F21, capital F22 up to capital F29. So, how one can make it, this capital F20, capital F21, F22 like this. So, how one can do it, when n is equal to 2, I mean 2 units, so when n is equal to 2, their equation 1 can be written as, it was actually f n x, capital F n x, so n is equal to 2, so it is f2x is equal to mean, it is y, then it is small f2y, because n is equal to 2, and this one your n minus 1, that is 2 minus 1, that is here it is, when n is equal to 2, it will be capital F2x is equal to mean y, small f2y plus n is equal to 2 f1 x minus y, right. So, this is equation 1. So, same thing we are putting here, that equation 1 we are putting n is equal to just 2, that is all, right. Now, this is the minimum, that means you have to combine all the minimum, but total load is 9 megawatt, Now, look, that means how many combinations are coming in a step of 1 megawatt. First is when y is equal to 0, say, then it is f20 plus f19, because x is equal to 9, right. Then when y is equal to 1, it is f21 plus f1 is 8 plus 1, we will have to 9, then comma, then f22 plus f1 your 7, right. Then f23 plus f1 6, then f24 plus f1 5, this is small f, capital F, right. Then small f25 plus capital F1 4, then small f26, 6 plus 3 9, you have to consider all the combination. So, your capital F1 3, small f27 plus capital F1 2, 7 plus 2 9, right, and small f28 plus capital F1 1, and small f29 and capital F1 0. So, all these combinations you have to make it, right, for these 2 units, because total demand is 9 megawatt. If you make total demand is say 20 megawatt for example, then how many combination will come, 0 20, then 1 19, 2 18, this way, I mean so many combinations, right. So, anyway, on computing, if you now everything you have to compute term by term, right. So, whenever we are calling that f2, that means this is the second unit, right. When here n is equal to 2 means small f2 means the second unit, right, and capital F1 is the first one, right. So, if you make all this combination, you will find this f22 plus f17, actually this is the minimum. That means only this part I will show you that what is f2, that f22 actually it is the second unit, it is the second unit. So, if you write that your what you call cost curve, that is your f2 is equal to this one, right, it is a2 pg2 square plus your b pg2, right. This is your from this data from this one, right. That means your a2 is equal to here is 0.80, say unit I am not putting, and your this one b2, this is b2 is equal to your 26.5, and then your this pg2 here f22 is the combination, that is 2 megawatt, that means pg2 is equal to 2 megawatt, right. That means you compute, that means your f22, that means f22, that is x is equal to actually y is equal to your 2 megawatt, that is y is equal to 2 megawatt, this one y is equal to 2 megawatt, right. Therefore, your f22, that is y is equal to your 2 megawatt, right. Therefore, f22 will be your a2 0.8 into your 2 square plus b2 is your 26.5 into your pg2 into 2, that is your f22, and whatever we are telling here, right, that this next is f17 for the unit 1, right, f17 is for the unit 1, that means for capital F1, making it here capital F1, right, for the unit 1, that is your x minus y, right, but total demand is given x is equal to 9 megawatt and y is equal to 2 megawatt, that means x minus y is equal to 7 megawatt, right. That means your F17, right, is equal to that cost characteristic first one, right. I write a1 pg1 square plus your what you call your b1 pg1, but pg1 actually 7, so pg1 actually 7, that means your here I am making it, that means your f17, that is your f17, actually this is your a1. So, we have this a1 is 0.385, we have already computed, right, 0.385 into your 7 square plus this b1 is 23.5, it is 23.5 into your what you call 7. So, whatever it coming, that means your combination is whatever you have got, the optimal combination is f29 is equal to f22 plus f17, that means whatever f2 value you get from here, right, and whatever you get from here, you please add these two, right, and this is coming rupees 239.565 hour. For the sake of completeness, I am making it. This is minimum, but you have to calculate all this only, all the combinations you have to compute. The way I showed one, you have to compute all these things, and out of which it is coming minimum. I am not just putting arbitrarily that this is minimum, right. I have computed all these things. After computing, I saw all this computation this morning also. I thought I should not show you here, right. So, it will kill a lot of time, right. So, but this is the minimum one, right. Suppose if it is given, suppose some assignment or something, we will not give you 1 megawatt. Suppose 9 megawatt, we can give you only 3 megawatt step change. So, in that case it will be 09, then it will be your 36, then it will be 63 and 90. So, only 4 calculations, 4 combinations, and you need 8 calculations, because here 1 1 2 each one. So, only 8 calculations. So, that will be result will be erroneous, but you have some feeling, right. So, that is a classroom exercise, you can make it, at least you will know how to compute, right. So, this is for first one, and that means this unit and this unit. If second unit generate 2 megawatt and first unit generate 7 megawatt, total is 9, then this is the minimum for first 2 units, right. Then what our objective will be, that second thing is, when you are adding the third unit, no, you have to compute, you have to your what you call compute f28, f27, etc., right. So, when you compute f28, f27, this is required actually. When you compute, similarly you compute f to 8. F to 8 means that just f to 8 you cannot compute. You have to take again the combination of 1 7, then 2 6, then your what you call 3 5, like this. All this combination you have to take the minimum of this, right. It is just not like I can compute your f to 8, right. You have to take your combination of 1 7, then your what you call 2 6. Similarly here also, when it is f to 7 means these all are actually minimum values. So every time you have to compute, you have to take the minimum values the way I showed you, that like this one, all these combinations you have to consider. For f to 8 also you have to take all combination, because this minimum f 2 is required. For example, why it is f to 8, f to 7, f to 1, when we are taking this minimum, for example, idea is using the recursive relation of if one can compute f30, f31, f39, right. Now suppose unit 3 is added, so f39, minimum is f30, that means we will take the cost characteristic of the third unit, that means this unit we are considering, this third unit we will take, right. And once you take this third unit, right, then you have to make f30, f29 minimum we have got it, just we have got it, no, this is the minimum, f29 minimum we have got it, this one is the f29 we have got it, this f29 we have got it. And f30 actually it is 0, because no general unit is not operating, that means in this case it is only 1 or 2 for f39. But when it is f31, you have to compute this your what you call this this one. When it is f31, that come to this this table, f31 you have to take this one, that a3 pg3 square plus b pg3, this thing you are compute for f3. So once you make f3, but look here f to 8 is coming, this f to 8 you have to take the minimum of all combination. That means here whatever I am telling, f to 8, f to 7, these are the minimum value, right. That means again you have to go for your what you call that f to 1 plus f to 7, like this you have to go, right, small f to 1 plus your capital F to your 7, like this, that I mean the way we have taken. And then that was 9 megawatt, that one will do for 8 megawatt, then 7 megawatt, and up to come up to this. And then every time you have to take the minimum, just cannot you take that. And just imagine that what is the, how much is the effort or what you call that computational effort. It is actually your sky high, the computation and your what you call in dynamic programming. But I am telling you that this is the philosophy, that means these are all actually minimum, everything you have to see which combination will give you minimum cost for unit 1 and 2, for which it is generating 8 megawatt, similarly 7 megawatt, these are all minimum. And those minimum thing f to 8, next one will come f32 plus f27, this f27 again minimum you have to take out of all combination 1 6 2 5, like this, out of which one is minimum, that one you have to put it here, then only you will get the good result, otherwise never, right. So similarly this way up to f39 plus f20, this way if you compute again you will find all these combinations have higher value than this one. So f39 actually giving f30 plus f29, that is rupees 239.56, this that means unit 1 and 2 still it is operating, right. Unit 2 is generating 2 megawatt, unit 1 is 7 megawatt, right. This is whatever we have got from here, this is unit 2 is 2 megawatt, unit 1 is generating 7 megawatt, right. So that is similarly if you proceed for similar way, if you proceed for f49, similarly again minimum f40 plus f39, like this, if you move like this, again if you make all sort of combinations you will get again this is the minimum. That means every time you can see that this is 0, f4 0 pg0 means that f4 will be 0, and f39 actually becoming actually f29, right, because this is 0, this unit is not generating any power, this generating is not even generating any power, every time this is coming minimum. That means to supply 9 megawatt, that unit 1 and 2 combination is the best one, right. So that's why examining f19, f29, f39 and f49, f49 also we have seen it is only one unit, not possible, it is 240 point something we have seen, right. For unit 1 here it is, here this calculation here it is, I will show you here f1 we have done it, here you have done it, and it is 242.68, so it is higher, right. So that means your only unit after combining all, this leads to the conclusion that optimum units to be committed for a 9 megawatt are 1 and 2, right, sharing load as unit 1 your 7 megawatt and unit 2 is 2 megawatt, and this is the best one, and minimum cost for that load is this much is coming, right, per hour, right. Although it is very high in reality, but this is some parameter has been taken per hour. In reality, this cost of generation power is not like that, it is very high, but some data has been taken, and just to show you that how things are, right. So, this is actually dynamic programming little bit, right, just how one can proceed, right. If you have any question when you will go through it, you can put the question in forum, everything will be explained, right. So, and with the increasing dependence of industry, now the reliability part, right, because reliability is another concern, very briefly will be explained here. So, with the again and how it is related to unit commitment, right. With the increasing dependence of industry, agriculture and day to day household comfort upon the continuity of electric supply, the reliability of power system has assumed great importance, right. In a power system, suppose it is just giving a simple logic, although if you install a large generating unit, say 500 megawatt generating unit, it will be installed everything cost, I mean if it's a single unit, it cost will be cheaper, but reliability will be less. Suppose if there is an outage 500 megawatt unit, so there will be shortage of 500 megawatt power, say, but if you install say 100 megawatt 5 units, right, of course your install cost, your what you call install cost and everything will be much higher, because individual 100 megawatt unit, it will be not same as your 500 megawatt, it will be much higher, but reliability will be more. If one unit is out, right, or 2 unit even is out, if 1 unit out, you can still supply 400 megawatt. If 2 unit is out, so at least you can supply 300 megawatt. But if only one 500 megawatt unit is there, if it is goes out, then 500 megawatt load you cannot supply. So, if you put that means if you put larger units, you have to see that your force outage or you know, any fault, anything happens, right, then you have to go for this what you call switch off that generating unit. So, loss of 500 megawatt power, that means that means reliability is less, although you are less expensive in terms of just a 100 megawatt unit you install, but if you will install that lower rating unit, your reliability will improve, right. That is the idea, right. But anyway, always higher rating unit is preferable, particularly day by day the cost of everything is going high. So, you have to see that its supply also 500 megawatt supply that power continuously, right, unless and until some abnormalities happen in the power system, right. So, every electric utility is normally under obligation to provide to its consumer a certain degree of continuity and quality of service, that is voltage and frequency, to a specified range, right. This is power quality. Therefore, economy and reliability, right, that is security, must be properly coordinated in arriving at the your what you call operational unit commitment decision. So, in order to meet the load demand under contingency of failure, say force outage, right, of a generator or its derating caused by a minor defect, say, right, the static your reserve capacity is always provided at a generating station, right, so that the total installed capacity exceeds the yearly peak load by a certain margin, right. So, in arriving at the economic unit commitment decision, right, at any particular time, the constant taken into account is merely the fact that the total capacity on line, total capacity on line is at least equal to the load. Total capacity on line means the generators, many generators are connected, right, it is connected and generating power, right, that those generation at least it has to be equal to the load. Sometimes we call the total capacity on line, right. Therefore, the margin, by margin if any between the capacity of units committed and the load is just is incidental, right. So, generally generation must supply load plus power loss, right, that is the idea, load plus power loss that generator will supply. So, if under actual operation one or more of the units were to fail perchance, say random outage, it may not be possible to meet the load requirements, right. So, to start a spare thermal unit, if it is a hydro, no problem, I told you, but if you do not have that facility for hydro, then if you start a spare standby thermal unit and to bring it on your what you call steam to take the load will take several hours, 2 to 8 hours, it takes time, right, just you cannot start thermal unit, right. So, that the load cannot be met intolerably long periods of time, that means that means you have to, there is no other way apart from making load shedding, right, because it takes time. So, therefore, to meet contingencies, the capacity of units online, the online means I told you the running units must have a definite margin over the load requirements at all time. The idea is, idea is something like this. Suppose that is what is the meaning? Suppose 5 units are operating, right, and suppose it is supplying your what you call 500 megawatt load, and each unit is generating 100 megawatt each. Suppose there is sudden outage of one unit, that means 100 megawatt is loss, right. Then 4 units are operating. So, load is your 500 megawatt, but generation is 400 megawatt, right. That means there must be some your what you call, sometimes is called that what you call the margin should be there. So, in the margin means suppose 100 megawatt generator, each one rating, but if suppose if every generator is rated those 4 units say 125 megawatt for example say, right, then other units, the other 4 units can somehow generate 125 megawatt each, such that it can accommodate the load of 500 megawatt, right. That is the meaning, that must have a definite margin over the load requirements at all time. That means if one unit is out, see that other running units can accommodate the load. Of course, if more units goes out, then it is not possible, but that means it can generate sometimes your what you call that over generation also 10-15% is possible by the generating units, right. So, whatever the rated capacity, it may be 10-15% more, it can generate power also, right. So, this is the idea, this is the meaning of that. The margin which is known as, this is called spinning reserve, right. Suppose a spinning reserve, I think I have told you in the power system analysis class, spinning reserve, suppose a generator can generate, suppose its maximum power generating capacity 200 megawatt, right, and suppose it was generating 160 megawatt. So, but if 40 megawatt load comes in, can take off, that means that excess 40 megawatt, sometimes we call this is a spinning reserve, right. That is the meaning of spinning reserve. Spinning means the machine is generating power, actually, and your what you call turbine generator is actually rotating, right, spinning. So, this is called spinning reserve, that machine is on online, that machine is on running, right. So, that ensures your continuity meeting the load demand up to a certain extent of probable loss of generation capacity. Because everything I have written for you, whatever I am telling from mouth, same thing is written here. So, you will go through it, it will be easier for you, right. So, while rules of thumb have been used based on past experience to determine the system spinning reserve and time. Of course, when you are working somewhere and you know that your what you call that operators are there at your power station. So, they are more experienced, right. You will find that their knowledge is really too good actually, because over the years they are handling that, and they know what time, I mean what kind of action can be taken at what time, they know it very well, right. So, Patton's analytical approach of this problem is very promising, little bit we will see. So, since the probability of unit outage increases with operating time, that means if operating for long time, then probability of outage also will increase, and since a unit which is to provide the spinning reserve at a particular time has to be started several hours ahead, right. That because thermal unit I told you 2 hours it takes. So, that means if you want additional unit, you have to start this thing unit much before that, right. The problem of security of supply has to be treated in totality over a period of 1 day. We will take the 1 day load curve, right. Furthermore, the loads are never known with complete certainty. The load is always uncertain. Look, in generally these are not the your topic for the teaching of this course. Load is actually it is uncertain, right. Generation is also uncertain, generation uncertainty, load uncertainties are there, but whatever little bit we are studying, it is completely deterministic, that means everything is certain, right. Also, the spinning reserve has to be provided at suitable generating stations of the system and not necessarily at every generating station. Suppose you have several power plants, no need that every power plant will have a spinning reserve, but some your what you call some of the generating station that spinning reserve should be there. Now, suppose this is a very complex problem, but we will take simplified problem. Look, a simplified treatment of the problem is presented here. Suppose upstate, downstate, right. These are uptime, T1 uptime, T2 uptime, T3 uptime like this. This is T1 downtime, this is repair, this is failure, this is downtime, this is time, this is upstate and this is downstate, because you do not know, some machines are on also off also. So, if it goes for your repair or when some outage is there, routine maintenance, right. So, these are uptime, this T1, T2, T3 may be different, they are not same, that is uptime, and downtime T1, T2, T3 also is different, not same, right. So, random unit performance record neglecting schedule outage, right. It is something we have taken 1 for up state and 0 for down state, right, I mean 1 or 0. So, a unit during its useful lifespan undergoes alternate periods or operation repair as shown in figure 1, right. This is your figure 1 alternate thing, right, but these are not uniform. My diagram looks like it is uniform, but this time is different, right, this different time, that is why I make T1 up, T2 up, T3 up, T1 down, T2 down, T3 down, they are not same, they may be different, right. So, the lengths of individual operating and repair periods are a random phenomena, with operating periods being much larger than the repair period. This is very natural. If most of the time is repair period, then how your generator will generate power? So, repair time is much less than the your what you call that operating time. Uptime is much higher than the downtime. When a unit has been operating for a long time, the random phenomena can be described by the following parameters. Say one thing is mean time to failure, we call mean uptime, right. This is mean time to failure. Then means T uptime, it is can be given as that sigma Tj up, sum up all the uptime, that is this thing, right, and divided by the number of cycles, because if you look at this graph, it should goes actually your up and down, right, up and down, it goes up and down, up state, down state, up state, down state. So, how many cycles are there, right. Say that is your T up is equal to sum up all the uptime divided by the number of cycles. So, this is equation 3. Similarly, mean time to repair, that is mean downtime, right, it is basically T down, capital T down is equal to sum all the downtime, right, then number of cycles. This is equation 4, right. Now, mean cycle time will be total will be T up plus T down, that is very simple, no. Here also from this diagram also T this all up and all down you add, that will be total cycle time, right. So, mean cycle time will be T up plus T down, very easy thing it is, right. So, inverse of this time can be defined as rates, that is failure rate lambda, right. This is actually my habit has become, right, lambda, actually lambda is like this, right, but this has become my habit. So, the power system analysis course also I told you when I started inductance, right. So, this is actually lambda is like this, but my habit has become like this, right. So, anyway, so if you ask me again and again and write, sometimes again I write this. So, this is lambda is equal to 1 upon T up, right, that is failures per year, the reciprocal of the uptime actually failures per year, right. This is your failure rate. Similarly, that repair rate, that is we define as a mu is equal to 1 upon T down, reciprocal of the time, and we call repairs per year, right. This is your repair rate. So, and then failure and repair rates are to be estimated from the past data of units. You have the past data, from that you have to see that, right, or I mean data are stored, I mean in the past all data are stored, or other similar units elsewhere by use of equation 3 and 4. Actually, in a power plant, suppose some fault has occurred, some generators are out, right. So, nowadays we have a huge computer database, all the solutions are available. Then you will find that if some fault has occurred to generator in any power station, then what they do actually, they record actually what type of fault it is and how it has happened, right. I mean cases how it has happened and how it has been, it was quickly or what you call restored that generator to the your what you call generator or transformer or whatsoever to that your system, right, online, right. All these things they have the storage, I mean what type of fault, anything, they have the huge database, right. So, anywhere if any such thing happens, immediately they go and verify what type of fault, and immediately they will see their database and immediately they know that what is the remedy for that, right. So, this is very common. It is for all the power companies, they have the huge database for all type of faults, and immediately they go to that quick solution. So, this is your because of nowadays computers available everywhere. So, we have all these facilities nowadays, right. So, sound engineering judgment must be exercised in arriving at these estimates. Of course, you have to see the data carefully. The failure rates are affected by preventive maintenance and the repair rates are sensitive to the size, composition and skill of repair teams, right. It is true repair rates are sensitive to size, composition, skill of repair team, that persons actually who are involved in this job, right, actually how quickly they can restore it. But you will find in those jobs people are most efficient, right. So many years back I saw one person in some power plant. He was expert in turbine. He's an engineer, right. He's an engineer, but maybe he's retired today, but I saw him that he knows turbine like anything, right. And like a labor, he actually works on turbine, right. He himself actually is a masterpiece of turbine. I have seen him working, and he knows every nut, bolt, everything of turbine. I mean, unbelievable talent he has. But remember, he is not your what you call mechanic or anything. He is an engineer, and as an engineer, he knows each and everything of the turbine. He is expert of turbine. I have seen him working also. Some unit was damaged and whole turbine has been opened. His mechanics or others are also there, supporting staff are there, but himself is working like anything, right. So you will find many such people in the industry, right. They are very dedicated for those works, right. If you go to the industry, then you will see how dedicated are they, right. So anyway, come back to this. By the ratio definition of probability, we can write the probability of a unit being in up or down state at any time. So P up is equal to probability T up by T up plus T down, that is total time, right. And we have defined 1 upon T up is equal to mu and lambda, and 1 upon T down is equal to mu. So you just substitute those, right. T up is equal to substitute your 1 upon lambda, and your T up and T down here also down 1 upon mu, you substitute, whatever you will get mu upon mu plus lambda. This is equation 5, that is probability P up, and P down is simply T down by the total your cycle time T up plus T down, it will be lambda upon mu plus lambda. This is equation 6. This is a very simple thing, and then P up plus P down is equal to 1, right. Total should be 1. Now P up and P down, this equation 5 and 6 are also termed as availability and unavailability respectively. This is the probability of the availability, right, and this is the probability of the unavailability, right. This is the thing, your simple thing. I have made it simple thing for you. While k units are operating, the system state your changes because of random outages, right. So failure of a unit can be regarded as an event independent of the state of other units. I mean, each failure is independent to other, such that it will be easier for you to analyze. It is not depending on other, right. It's everyone is an independent state, because we are little bit we are talking about probability. So we are assuming that it is independent of the other units, right. So if a particular system state I, set I state, is defined as say capital X suffix I, right, units in down state and capital Y suffix I in up state, where k is equal to xi plus yi, it is fine, right. Then the probability of the system being in this state is, it is product j belong to yi, that means units which are belong to up state, right, that is yi in the up state units, right. That is, you have to make the product, you have 3 units, the probability of all this thing you have to multiply, then into again product of your units L belong to xi which are in down state, right, L belongs to xi into pi, this is down, right. This is equation 7. This is a product. It looks like is probability and product is a very simple thing, actually very simple thing, right. So now, so pattern security function. So just we will explain, right, many things we will assume here and just explain, and with completing this we will complete the unit commitment and this course, right. So a breach of system security is defined as some intolerable or undesirable condition, that is breach of system security is known, right. So the only breach of security considered here is insufficient generation capacity. So here we will consider the insufficient generation capacity, that is your only breach of security. The pattern security function, which qualitatively estimates the probability that the available generation capacity, that is sum of capacities of units committed, that means which units which actually are on running, right, at a particular hour is less than the system load at that time, is defined as S is equal to sigma pi Ri, right. So sum of capacities, that is the probability that the available generation at a particular hour, right, is less than the system load at that time, is defined as S is equal to your sigma pi Ri. This is equation 8, right. Now what is P, what is R? Now Pi actually probability of system, right, being state I, right. This is the probability of system being in state I, that is C equation 7 I have written, that means this equation, this is the equation, you see the equation, right. So it is your from this product of this probability, right. So, and Ri, the probability of the system state I causes breach of system security, right. So, these two data if is known, then we can compute. When system load is deterministic, that means no uncertainty is there, that is known with complete certainty, no uncertainty is there, then in that case Ri is equal to 1 if available capacity is less than the load, right, and it is 0 otherwise, either 0 or it is less, right. And second thing is S indeed is a qualitative estimate of system insecurity, that is sigma pi Ri, right. Now, though theoretically equation 8 must be sum over all possible system state, because sigma pi Ri P1 R1 plus P2 R2 like this, from a practical point of view the sum needs to be carried out over states reflecting a relatively small number of units on force outage. Example, that is states with more than 2 units out, or maybe I mean states with more than 2 units out, it is very rare, right. And second thing is may be neglected as the probability of their occurrence will be too low, because 2 units outage probability is very low. So, we may neglect it, right. But if you want detail, then perhaps you can do it, but 2 units 3 units, do you think that will be totally out together? If it happens, then you have to, but probability will be less, right. Now, security constant optimal unit commitment, I will give you a simple example here. Once the unit to be committed at a particular load level are known from your purely economic consideration, the security function S is computed as per equation 8, means S is equal to sigma pi Ri, right. So, this figure should not exceed a certain maximum tolerable insecurity level. This will be defined by you, right. That MTIL, that is maximum tolerable insecurity level, will be defined by you, that is MTIL, right. For a given system is a management decision which is guided by from the past experience, that you can define this value MTIL, that is maximum tolerable in your insecurity level, right. So, if the value of S exceed this one, then the economic unit commitment schedule is modified, right. I mean if your value suppose you have defined this is say 0.0005 and the value of S exceeds MTIL, right, and S is becoming say suppose it is for example it is 0.05 and it is 0.06. So, it is exceeding this one, that means you whatever condition you set, it is not matching. So, you have to rethink, you have to go for second iteration, something like that. The economic unit commitment schedule is modified by bringing in the next most economic unit as per the unit commitment table. So, S is then recalculated and checked, the process is continued till S becomes less than MTIL, right. MTIL you have defined, right, and it has to be less than equal to like this, right. But after your unit commitment thing, you can check this. As the economic unit commitment table has some inherent spinning reserve, rarely more than one iteration is found to be necessary. That means, when you check this, hardly one iteration this can do it. So, how we will do it? For example, suppose this is actually your unit commitment table, this is that optimum unit commitment table, this has been given. So, after unit commitment, suppose this data is given to you, suppose this is that unit commitment table, how it operates. We have taken a very ideal case, this is the load curve A, B, C, D, E, this is I have forgotten to write, this is E and this is F, right, A, B, C, D, E, F. So, each load level we have taken, it is a 4 hour each. So, total 24 hours, this is time. So, A, B, C, D period is given. So, when peak load, when A is equal to 4 peak load, right, sorry, this 4 hours, when this is a peak load A period, it is 0 to 4, say first 4 hours, it is maybe from mid noon to your what you call next day mid noon, it is not like a 0 hours, it is some time, right, something is taken, right. So, question is that during this period that all the units are operating, all the 4 units are operating, but during B period it is 15 megawatt, all 3 units are operating and 1 unit is off, and for your when 10 megawatt, right, C period only 2 units are operating, and when D period again it is 3 units are operating, it is not operating, and E period only 1 it is operating, which is 5 megawatt, and F period only 2 megawatt 2 units are operating because it is 10 megawatt. It is ideal case I have taken, right, and this is your unit after unit commitment set dynamic programming and whatever method, this is your unit commitment table at every load level. This is load level A, B, C, D, E, F, right, and this 24 hours load level is taken. So, now everything is written here. Consider a 4 unit example daily load curve for this system given in figure 2. This is figure 2 and this is the table. Economically optimal unit commitment table for this load curve is given in this table. This is also given corresponding to this load curve. And let us now check if the above optimal unit commitment table is secure in every period of the load curve, right, whether it is not. So, what we will do is, for the minimum load of 5 megawatt, first I will check minimum load POD of figure 2. This is the minimum load 5 megawatt, this is 5 megawatt, and that is a POD, right. According to the optimal unit commitment table, only unit 1 is to be operated. As per the unit commitment table, that only this is the period, only this unit is operating, only one unit, right, that is unit 1, this is the unit number, unit 1 is operating, other units are off, right. So, therefore, assuming identical failure rate for all the units, we are assuming their failure rate is identical, that is lambda of 1 upon per year, right, and repair rate mu will be 99 per year, right. This is your failure rate and this is your repair rate. Some arbitrary data has been taken, right. So, for all the 4 units, let us check if the system is secure for the period. That means, what does it mean? That from unit commitment, that only when load is 5 megawatt, this only one unit is on, and this table actually prepared from the same data earlier. So, minimum generation is 1 megawatt, maximum is 12 megawatt. So, it is 5 megawatt. So, one unit is operating. Now, so further assume that this data has been given to you 0.005, MTIL is given, right. I told you earlier, right, that is your this is a decision from the management, that maximum tolerable insecurity level MTIL, right. So, this data is given to you and you have to check S is equal to PIRI. So, unit 1 can be only in 2 possible states, either operating or on force outage. That means, it can operate, or force outage means 5 megawatt load cannot be supplied because all the units are off. So, in this case, this S is equal to 2 units are there, we have to check for 2 units, 2 states, I is equal to 1 to 2, PIRI is equal to P1 R1 plus P2 R2, right. So, in that case, what will happen, that P1 is equal to P up, right, 2 states will do. So, it is mu upon mu plus lambda is equal to your 100 is coming, this is 0.99, because data is given here, mu is 99 per year and this is 1 per year. So, P1 is and R1 is 0, because unit 1 is 12 megawatt, which is greater than 5 megawatt. So, generation is what you call much more than the load, right. So, R1 is equal to 0. And similarly, P2, the downtime is lambda upon mu plus lambda, that is 0.01, because lambda is actually 1 per year. So, 1 upon 100, so 0.01. So, R2 is equal to, with unit 1 down, so R2 is equal to 1 and load demand cannot be met. So, now you compute S is equal to then P1 R1, that is 0.99 into 0, whatever we have got here, P1 R1, then P2 R2 plus P2 R2, 0.01 into this thing, that means 0.01 greater than 0.005, that is your this MTIL value. Therefore, thus unit 1 above your alone supplying 5 megawatt load fails to satisfy the prescribed security is criteria, because we have to bring this one below 0.005. That means, although you have got the unit commitment, but you have to check the security also, right. So, fails to satisfy the prescribed security criterion, because S actually whatever value of S, it should be less than equal to MTIL. Then what we will do, we will choose the next unit. So, in order to obtain the optimal and yet secure unit commitment, is necessary to run the next most economical unit, that is unit 2 along with unit 1, right. Now, with both units 1 and 2 are operating, security function is contributed only by the state when both the units are on force outage. So, in this case, the state with both units operating or either one failed can meet the load demand of 5 megawatt and do not contribute to the security function. Therefore, that S is equal to can be taken as P down into 1, right. That means, it will be actually, that means, this one your what you call that R is equal to your what you call that 1, right, and you have to consider your what you call, this is another unit you are putting. So, its probability is 0.01. So, 0.01 into P down into P down. So, 0.01 into 0.01. So, it is 0.001, and therefore, this is actually, this is actually your less than your what you call 0.001 less than your what you call what you have defined, that is 0.005, that means 0.005, that means your criteria is satisfied. So, just nothing, but put at unit and follow the same procedure, and this is for classroom purpose only I have made it. In reality many issues are there, many constraints are there, right, so many issues are there. So, with this this power system engineering course, just 1 or 2 minutes briefing, then it will be this thing. So, I will suggest that you please go through all the notes and everything. Those who will listen to the last lecture, I will tell that particularly the distribution load flow, everything has been given in detail, right. So, please write down everything, and solution methodology is also very easy, right. And for that a lot of effort has been given to generate that, write those things, and everything was made, all hand calculation, everything, all the numericals, everything, all by your this person only, right. So, if you have if you find any calculation error or anything, you please send the mail or put the question in the forum. We will give all the answers to you, right. I mean all the answers, and whatever has been made, starting from your insulator, then your cables, then everything. Only one thing I forgot to show you, that particularly in the corona loss, that is insulator thing I showed you, that for your V type your connection for insulators, I will show you the how corona happens, some good photograph. I completely forgot to show you that photograph. If possible, some corona photograph in the forum or somewhere, I will ask my TAs, they will upload it, right, they will scan it and upload it. You can have a look that how corona happens. I forgot it, I recall I forgot it, right. So, rest of the things, I hope things will be quite easier to you, and please just go through it, and if you have any doubt or anything, you please send the mail. I will reply, or I will ask my TAs also to reply on behalf of me. And this is a very 30-hour course, means actually in the classroom that it will be nearly doubled, right, because here nobody is sitting in front of me, and but I am imagination, I always think the students are sitting in front of me, and that way I tried. And if you have any clarification or anything of this course, please send mail to me, right. So, thank you very much, and I do hope you will you will listen all these video lectures. So, thank you very much. Thank you.